What we are going to develop in the next few slides is a per-phase equivalent circuit of an induction motor. Each parameter models a physical effect inside the motor, such as resistance, leakage, magnetization, and power transfer. The stator winding can be represented as shown here. Note that there is no difference in form between the stator equivalent circuit and that of a transformer primary winding. The only difference lies in the magnitude of the parameters. For example, the excitation current I0 is considerably larger in the induction motor because of its air gap. The applied stator voltage V1 is shown here. This is the stator input current, I1. The stator copper losses is represented by R1, and X1 represents the stator leakage reactance. The stator side of the motor includes the applied voltage and input current. The stator resistance represents the copper losses, and the leakage reactance models the flux that does not link with the rotor. This represents the magnetizing branch of the motor. I0 or I0 represents the no-load current. RC represents the core loss resistance, while XM represents the magnetizing reactance. The magnetizing branch accounts for the iron losses and the magnetizing current. Core loss resistance represents the iron losses, while the magnetizing reactance models the flux needed for the motor operation. This is the air gap voltage. At the air gap, the stator induces a voltage proportional to the rotor's induced voltage. This air gap voltage is linked between the stator and the rotor circuits. The rotor winding can be represented as shown here. This is the air gap voltage. At the air gap, the stator induces a voltage. This air gap voltage is the link between the stator and the rotor circuits. I2 represents the rotor current. X2 represents the rotor leakage reactance. R2 all over S represents the rotor resistance over the slip. The slip is calculated by the synchronous speed ns minus the actual speed n of the rotor, and that is divided by the synchronous speed ns. Note that the effective resistance changes with slip, modeling the rotor copper losses and power conversions, while leakage reactance represents the rotor flux leakage. The equivalent circuit of an induction motor is obtained by combining the stator and rotor equivalent circuits as shown here. Note that the form of the equivalent circuit is identical to that of a two-winding transformer. The slip is the key performance factor. It measures how far the rotor lags behind the synchronous speed and directly determines the torque and the power delivered by the motor. The term A is the turns ratio of the motor, similar to that of a transformer. It's defined as A equals to N1 divided by N2. N1 is equal to the number of stator turns and N2 equals the number of rotor turns. Because an induction motor works like a rotating transformer, we often refer the rotor circuit to the stator side. Using A, rotor voltages, currents, and impedances are scaled like this. For voltage, E1 is equal to A E2. For current, I primed 2 is equal to I2 divided by A. Reactance, X primed 2 is equal to A squared X2. And resistance, R primed 2 is equal to A squared R2. These terms come from the fact that the rotor resistance, when referred to the stator, must also be modified by the slip S to model real power transfer. This term is usually split to emphasize the fact that R'2 is made up of two parts: rotor copper losses, a fixed part, and the mechanical power converted to the shaft, which is a variable part that varies with the slip. Even though a squirrel cage rotor has bars instead of coils, mathematically we can still treat it as if it were a wound rotor with a certain number of effective turns. The effective turns, N2, are defined so that the air gap magnemotive force, MMF, produced by the squirrel cage equals the MMF that would be produced by a wound rotor with N2 turns carrying the same current. In other words, N2 is not a physical count of bars, but an equivalent value used to model the caged rotor as a transformer secondary. Manufacturers and motor designers compute the effective turns ratio, A, or N1 over N2, during the design. Ready to go beyond just solving problems? If you've been following my daily post and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available, or soon will be, on my official course site, my stand store for electrical training. Just go to the web address that you see at the bottom of this slide, https://stand.store/GVB. In recent years, the reality of climate change has become impossible to ignore. Severe weather events are growing more frequent and more intense. For homeowners, this means that utility power outages are no longer inconveniences. They can last for hours, days, or in extreme cases, even longer. The question is no longer if, but when. You'll need a solution to keep your homes powered and your family safe. Now is the time to prepare and ensure that you're not left in the dark when the next storm hits. Here are some trusted resources to help you prevent power outages at home. Jackery Canada at this web address, Jackery USA at this web address, Bluetti Canada at this web address, Bluetti USA at this web address, and Bluetti Australia at this web address. And finally, you can get EcoFlow at this web address.